So during the previous class, we talked about the data types, right? And then we kind of also talked, mentioned several of them, as for example int, which is just like a number, and then for example double, which is also a number but not necessarily full, as something like this. And then we also talked about char, which is like a character, as this. And then string, which is like several characters in a row, as marking. And then float, which is also not full number, float, decimal number. Right, and so on. So what's the difference? What is the difference between all of this, and how, for example, float is different than double, if they also, all of them store decimal numbers, right? And we also have, let's say, the amount of bits in every single one, and then the limitation of the maximum number it can store. As for example, for int, it's 32 bits, and it's up to basically from minus 2 power 31. Sorry, yeah, minus 2 to power 31. But then, for example, for the long, which is also the same type of numbers, right? It's not from these, but it has 64 bits, and it's from minus 2 power 63 to 2 power 63. So basically we have a question, why, right? How does this even work? Why is it like these exact numbers, and basically how it works? So in general, in computer machines and everything, how does even computer work, right? So they have two states, as turn on and turn off, electricity on and off. And with this logic, they also store numbers. For example, for us, we have the decimal representation of the numbers, 1234, right? Which is 1 times 1000, right? Plus 2 times 100, plus 3 times 10, right? Plus 4 times 1. And then, for example, if it's 21,000, it's 2 times 10,000, plus so on, right? This is the decimal representation of the numbers. But in computers, they don't store numbers like this. For computers, they only can have ones and zeros. For example, 1, 1, 0, 1. And how do we understand this? Do we know which number is it?
1 times 2, 3 plus 1 times 2 square plus 0 times 2 plus 1 times 1.
That's correct. So basically, for the binary representation, let's say we can imagine the indexes over here, starting from the right side, 0, 1, 2, 3, right? And then, as we did over here, for example, we multiplied also 0, 1, 2, 3, 4, right? So we multiplied 2 times 10 power of 4, and then plus 1 multiplied 10 power of 3, and then addition 2 times 10 power of 2 and so on, right? So with the same logic, the binary system works too, as it's like 1 times 2 power of 3 plus 1 times 2 power of 2 plus 0 times 2 power of 1 plus, because it's like 0, right? And then 1 times 2 power of 0. And then this is 8, this is 4, this is 0, this is 1, right? And then we get overall sum 13. So the binary representation of 1101 is the decimal of 13. Right? Mm-hmm. And then now, as we note that like how let's say binary numbers work, let's talk about like how we can convert from. So we already saw that we can convert from the binary to decimal, right? How can we convert from decimal to binary? Like for example, let's say we have 17.
17 equals to 1 times 1 plus, maybe we should go from the large side, 16 plus 1. So it is 1 times 2 square 4, 2 power 4 plus 1 times 2 power 0.
That's correct. Okay. And then let's say we have like we have given like a number of decimal, just some number n, right? And then we have to convert it to binary. But we can't like see like, okay, it's like 16, How do we write a code that will convert from decimal to binary?
Let it decide if this number is larger than the largest 2 power blah blah blah, and then start from that. Let minus some the smaller ones and decide if it will receive a positive number. If that is, it will record that number and keep the cycle.
So you're saying we find the maximum number of power 2, which is less than the number over here, and then we divide, and then we continue doing the same thing.
Yes.
That's a good approach, but for that you have to find the maximum, blah, 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 blah. It's not efficient. So other than that, what we can do, let's see. So let's say we have the 13, right? We have to convert 13 to decimal. To binary. So 13 is like 1, 1, 0, 1, right? Okay. And then, okay, let's see. Is it odd or even, the number?
Odd number.
Odd number, right? It's odd. Can you tell me like what part of the binary representation shows if it's odd or even?
The rightmost part.
The rightmost part, correct. Because it's like either 0 or 1, right? And then these are already like power of something, like 2, and then they're like even, right? So only because of these, the odd even changes, right? So if we do, for example, 13 modulo 2, do you understand this? If we do 13 modulo 2, 1. So, and then for example, if we do 14 modulo 2, 0. What is this? The rightmost, right? So we can access, let's say, the rightmost element with just modulo 2, right? So, okay, let's say we have the 13, right? So we did like modulo 2 and we see it's like equal to 1, right? So let's say we are building, let's say we're building the our like binary representation. So we have 1 here, right? What about this one?
13, 12th model of 2 power 2.
12 modulo 2 power 2
Is 0.
is 0, right? Okay, let's continue. Let's say, what's next?
13 model of 2 power 2.
For example, there it comes like,
It should be 12 model of 2 power 3.
12, sorry, yeah, equals
1. 0. Ooh. Why is it
right?
4?
Why is it 4? Because by doing modulo 8, basically, like for example, when we got 1 here, right? We deduct it from 13, right? And then we have 1, 1, 0, 0, right? Left. Because we did minus 1. Right? And then when we do modulo 8, we are looking not to this one, or not to this one, right? Or not to this one. We are looking from here, this number. So what we are going to do is, after doing modulo 2, and after getting this number, either 0 or 1, doesn't matter, we are going to divide 13 into 2, which is equal to 6, right? And division, like dividing by 2 in a binary system, basically means just erasing the last digit. Because like you just make everything twice less, right? It's like 2 times k, 2 times k minus 1, and then the 2k just with division of 2 just moves over here, this moves over here, this moves over here, this moves over here, this moves over here, and then this character over here moves outside, it just disappears. Right? It's a shift. So with the shift that we do, so we got this, right?
And then 13 divided
And then we
by
just shift, right? So our number becomes this. And then we can also check the result modulo by 2. And then we get 0, right?
And then 3 modulo by 2.
Yeah, and then we divide it by 2, so it's 3 modulo by 2, which is 1, right? And then we divide it again by 2.
1 modulo by 2.
1 modulo by 2 equals to 1. So we got 1, 0, 1, 1. We converted the decimal from, basically we converted decimal to binary. And then this thing works not only with 13, basically it works for any number, right? So later on we'll, let's say, like write the code for actual thing, because so far we don't know like force cycles and stuff, so we can't write the code, right? But this is the logic behind how this works. Okay, let's see. And very interesting thing, after we understand like the binary representation and everything, let's try to understand why do we have the limits for the, for example, int or long, right? It's again the decimal, like we just have like normal whole numbers, right? And for example, for int, it's 32 bits, right? And also 8 bits is equal to 1 byte, to just It's like 32 bits or 4 bytes. So we have 32 bits, right? And can we try to guess what numbers can we store based on knowledge of
2
having?
power of minus 31 to 2 power of 31.
Or why 31, not 32?
Because 2 takes 1 bit.
Because what?
2 takes 1 bit.
Minus takes 1 bit. So basically, we have minus 231 to 231, right? So 31 of the bits store the. It's not actually like this, but we can like say like this. So 31 of them like store the number, and then one goes to also support the sign, right?
I totally understand.
And then same for the long, right? Which is like double the size, Like it's 8 bytes and 64 bits, right? And then basically, what is the limit for long?
Minus 2 power of 63 to 2 power of 63.
Yes, that's correct. Actually, there's a catch. It's either like this or like 263 minus 1. Let me check. Wait. So basically, I'll explain. Okay, never mind. So, okay, another thing to know is we have both int and how is it called? Sorry. We have it like in the previous lecture. It's here, right? Over here.
I understand the minus 1. It's like 999 is 1000 minus 1.
Just a second. It's over here, right? Is it? So here we can see that yep, unsigned. Sorry, yeah, unsigned. So, for example, signed int used for integers equivalent to int, right? And then unsigned int can only store positive integers. And let's say we have unsigned int, right? Unsigned. And it's also 4 bytes and like 32 bits.
So it can go from 0 to 2 times 62.
0 to 2 times 32? Or
minus 1.
minus 1. Why? Because we have, let's say, like the binary representation of the, let's say we have like 32 bits to fill, right? Let's try to get the maximum, right? Everything is 1, so on, right? 32 ones. And here is like 0, 1, 2, 30, 31, right? Because we start from 0, like the index. So it's like 231 plus 230 plus 239 plus plus 2, not sorry, 20, right? Is it equal to 232?
No.
No. Is it equal to 232 minus 1?
Yes.
Yes. So that's how we get the minus 1, right? Let's see the limitation for the so we have like this number, right? It says like from this to this. So if we so 2 power of 31 is this much, right? So basically,
Why is the minus part doesn't have minus 1? Oh, +1.
Because it basically is divided in some way. Let's say it's like minus 231, right? Up to 231 minus 1, right? And then let's say we have in the middle 0, right? Right? The 0 is with this, and minus 1 is like with minus 1, and they have the same portion, right? Okay. This is it. And then let's also see how we type the. It's not really that used. It's like unsigned int, for example, right? Oh, sorry. What? Oh yeah, number. Okay, let's see. And then let's say int is 0, right? The unsigned int. Like the limit is from 0 to 2 power of 32 minus 1, right? What will happen if I do number minus 1? Like if I try to deduct 1 from number, which is 0.
Minus 1 from 2 power 32 minus 2.
Let's see. Okay. Count number minus 1, right? Okay. So it gives us which is sorry. We got 2 power 32 minus 1, right? How? Basically, it's kind of a cycle. Like numbers are like 0, 1, 2, 3, so on, so on, so on. 2 power 32 minus 2, 2 power 32 minus 1. This is our limit, right? This is the beginning, this is the end. Minus 1. Like we move like one step, right? Like from 1, if you do minus 1, it goes from 0, then from 0 it's like. But then, basically, we try to avoid these type of things. As for example, the same happens for like regular int. If we try to store like greater number than this, than the limit, we are going to encounter a situation of just random number appearing. something unpredictable. This is called like overflow. Like we get over the limit, right? So that's why for big numbers, we have big long log, for example, which is twice the bit size, and then it's up to 2 power of 63, which is actually so much more, right? Let's say 64, doesn't matter. That's 63. We can store 9 times 10 power of 18, right? This is good. And then the difference with Python is that Python actually has like implemented like support for bigger numbers, like in the Python already. But then that support works in a different way. It's not all one, right? It's something different. We'll cover it later. Okay. Let's see what else we have. So in the plan we also have like, and also the same for float and double, right? So for float and double, what is the difference between float and double?
Double has 2 decimal places.
Again?
Double have 2 decimal places. Like 2.50.
2.50. What do you mean? Can you show? So double can store more. It's called like significant digits. Basically, like it has more capability of storing greater precision, greater numbers, and everything, right? So if we're working with very like precise numbers, like after the point, that's like, I don't know, 1.0000000000000. We have to use double because otherwise we'll have, let's say, some margin, some error. If we do it like with less capable data type as float. There are some, let's say, not tricks, but like some flaws. For example, for double, like, I don't remember which example was it, but like, let me try. Double number equal to 1,0,0,0,0,0,0,0,0,0,0,0 times power of 9, then times, no, sorry, and then we do number time equal and then we try to see out the number. What do you think it will bring?
10 times 18. 10 power of.
Yeah, yeah, right? Because it has like 63 bytes and stuff, and as the long, right? Oh wait. Nope. Sorry. Pause. Never mind. Basically, this would answer maybe 10 power of 18 plus 1.
Oh, why? Let's see.
Because of the way that the partial numbers are implemented. You can store very, very big numbers as 10 power of 300 something. But then it's a cost of the precision. So yeah, it's just for later. We can discuss. So, as we know about the binary representation of the numbers, we can today also talk about the bit operations. Let's write down the bit operations that we have. One is AND, like OR, XOR, yeah, not left shift, right shift. So let's see what each of them does. Right. So let's say we have like a binary number, again like 1, 1, 0, 1, right? And then we have another binary number, which is, let's say, 1, 0, 0, 1. No. Yeah? No. Let's have 1, 0, 0, and then have 0, 1, 0. This would be better. So, we can perform, for example, binary operations. Hello. You can come and sit over here. So because we're not really many this time, so I decided that. Also the projector doesn't, I don't know why, but. So, we can perform like binary operations between two of them, right? Binary operations are, for example, like we have operations like plus, minus, like multiplication stuff, right? But binary operations are for the binary system, right? Like they operate in a way of binary. So, let's say we have like one. We'll like let's say draw the tables for each of the operation. As for example, let's say we have two numbers, right? First, second, and then we have like 1, 0. Sorry, no. 0, 0, 1, 0, 0, 1, 1, 1. All of the cases, right? All of the combinations. And then for every single operation, there is a logic behind. For example, AND only gives one output, like 1, when both of the inputs are true. Which means for AND to be 1, both of the numbers needs to be 1, right? So this is the result of the operation. And then for AND, for 0, 0, it's 0, because none of them. For 1, 0, it's also 0, because one of them is 0. For 0, 1 is also 0, and then for 1, 1, it's 1, right? This is AND. for or, let's draw the table again. For or, the result is 1 only if any of the input is 1. So in 0, 0 it's 0 because nothing is 1, but then in 1, 0 at least 1 is 1, so it's 1, 0, 1, 1, 1, 1, 1, right? For XOR, we have, it's like excluding OR, right? For excluding OR, it's the same OR, but in case of having 1, 1, it becomes 0. So 0, 0 is 0, 1, 0 is 1, 0, 1 is 1, but then when we have 1, 1, it's 0. For not, the, like, is a bit different. Not just flips every single bit as 0, 1, 0 becomes 1, 1 becomes 0. Not. It just flips, right? And then for the left and right shifts, right? We already talked about example of a shift before when we were like converting decimal to binary, right? For example here, do you remember? Right? It was kind of a shift, right? So the operation shift is actually doing the shift. So it says slice the bits left for the left shift. Each step multiplies by 2, basically. And then slice the bits right, each step divides by 2. Integer division. So, for example, if we have like a number of, again, 1, 1, 0, 1, right? It's the 13 decimal, right? So if we do 13 left shift 1, which is like 1 bit shifted, right? 1 shift by 1. But we'll shift everything over here and we'll have 0 over here, right? And every single multiplication here is like times 2. It was like 2 power of 3, it became 2 power of, no, sorry, was it 1, 0, 1, 2, 3, 4, right? So it was 2 power of 3, it became 2 power of 4, right? Because the index is changed. It's basically like just multiplication of 2. No, so 26. And then if we do like 13 shift 3.
13 multiplies by 8.
Correct. Right, which is
104.
right. So in that case, we just shifted 3 bits, and like it's like this, and then it goes like this, and basically we just get like 0 over here, and then the next time 0 over here, 0 over here, right? And then by the end we have the same number, just times 8, the power of the shift, right? And then for right shift, right? This was the left shift. For right shift, sorry. right shift. Again, with the same logic, we have, for example, some number, like 1, 1, 0, 1, again. 0, 1, 2, 3. And then, if we do, for example, shift of 1,
Well, this one just totally disappeared.
yes, so we get integer division by 2, which is 6, right? And then, for example, if we do like 13 move 3.
Integer divided by 8, 1.
And then basically we just get rid of like this, and then we just have like basically every single time, like for example, one time we do it, it becomes like 1, 1, 0, and then one time more it becomes 1, 1, and then one time more it becomes 1. It becomes 1, right? And then if we do like 13 shift 10,
0.
it will just become 0, right? And for example, this was like the right shift, right? If we do like the left shift over here somewhere, yeah. Here? Yeah. The left shift. If we do like 1 shifted 30.
2 times
Power of
30.
yes. So if you need like to access like for example 2 power or like some power of 2, for example big top power like as 2 power of 30 for example, instead of like doing like like multiplying through 30 times each time and spending like operations, you can just do 1 shift 30, which is all 1. It's an instant operation instead of like multiplying it each time, right? Let's see what was behind. We can look to some examples of the operations in code, right? So let's go. If you have like int a12, int b12, right? 10. Sorry. And here 12 is 1 1 0 0, and then 10 is like 1 0 1 0, right? If we do like cout, let's say cout, A and B. What? Yes. What we'll get?
8.
Because we'll get like here 1 1, it's 1, and then other just becomes 0 because they are not 1 1 each. So which is 8. And then let's say we get A or B, right? What will we get? Don't look over there. Let's try to
1 1 1 0.
Which is
14.
yes, that's correct. And then if we do like XOR B,
0 1 1 0.
0 1 1 0. Good job. Which is
6.
And then if we do let's say shift, A shifted by 1 will get shifted left.
Oh.
Like this sign, you just imagine like moving it over there, right?
24.
So we'll get 24, which is like 1, 1, 0, 0, and then shift another 0, 24, right? And then for shift over right side, we'll get 6 division by 2, right? 1, 1, 0, and then the rightmost bit just gets destroyed. And then we can try to run to see. Everything's fine. Nice. So some tricks. For example, even or odd. How can we how can we like, for example, find out if the number is odd or even with the binary operations?
See the rightmost letter.
Yes, but with binary operation. Like we have some number as, for example, let's say 13 again. In C equal to 13, which is in binary 1101, right? So how can we check if the number is odd or even with binary operation?
The last number.
The last number, yes.
If it's zeros, if it's ones.
Yes, yes. So how do we check if it's 0 or 1? We could do the modulo too, right? For example. Yeah. But for example, with binary operations, we can do, let's see, we can do C, which is the number, and 1. Right? So what are we doing is basically, and 1 is 0, like just 0, everything 0 and then 1 at the very end. And then the only outcome possible from this is either 0 or 1. If the last bit is 1, we'll get 1, and the last bit is 0, we'll get 0. Right? So we can try, for example, with C and A. Here we can see with C, which is 13, it gave 1, and then with A, which is 12, it gave 0. Right. Okay. And then the same thing as like the multiplication division with the shift, right? So if we shift to the, as we saw here, if we shift to left, we get times 2, right? Because we generate 1 bit over very beginning of the bit string. And then if we do shift to right, we just destroy the last bit and everything shifts, and then it's division by 2, right? And again, very nice usage of the bit operations. For example, you have to, like, you have some number, like a big number, let's say int x equal to pop, right? Can you tell me, for example, what bit you have at, let's say, 10th index of bit operations?
Try C and
like
1
index.
0 0 0 0 0 0 0 0.
How do we see that?
If that digit is 1, it will happen to be 1. If it's not, it will be 0. And then we can test by OR and XOR.
So, okay. So basically, to see if the 10th index is 1 or 0, right? We can try to do what? We can try to do x the number, and with another number. So imagine you have like some numbers, right? Some numbers, something, and you want to check this bit if it's 0 or 1. You can just generate a number which is all 0, right? And then the bit that you want is 1, and then the others are 0. And then if you perform AND operation, you'll either get a 0 or the bit by itself. So to do that, we have 1 shifted what? Don't look up. 10, right? We moved 1 10 times. Alright? Yeah. We'll move 1 10 times, and then we have the 10th index 1, and that's it. Like everything else is 0. And then if we do it like AND with x, you'll get either 0 or the number. Alright, let's try. We got the number. So there's 1 bit in a 10th index. So that's why we got like 1024, like, which is 2 powers of 10, right? Okay. I think we're going very nicely. From the data types, we also can cover just in very short. Basically, we also have like other than this basic. Oh, I erased. Other than the basic data types, like the int, char, long, double, float, and everything, we also can support pair. Pair is, as it says, a pair of 2 variables. For example, the syntax for this is pair, the 2 things, like I don't know how it's called. And then we write down the types that we will use in a pair. Let me show you. Int, let's call it key, equal to this type of brackets, 2, 5. Now we have key variable which has access to 2 numbers. Look, if we write down key dot, we can access to the first or to the second. Right? So if we do like cout p first, space, and then p second. So we'll get, we'll get 2 and 5, right? And with the same logic, we can have not only int, we can have, for example, int and double. And the first element will be int, and the second element will be double type. So we can store, like, for example, something like this. Look. And then with the same logic, the pair can also host another pair. We can do pair, right? So pair, which has int, and for example double. Which means the first element will be pair and the second element will be double. So if we try to access the second element, we'll just see second, right? But if you want to access the first element, we'll see first, and after that, first and second. So we go basically like it's the first, it's the second, And then if we have something else here, we also go first or second.
Can it give me the entire pair?
Hmm?
Oh.
Yes, or yeah, it can give also the entire pair.
Hmm.
If we do only like one first, we will just get the entire pair. And then we also have struct, but I won't tell about that, I think. Like basically we can also host like, okay, we can also host other data type, which is our own. We can like build our data type, which is called struct. And the syntax is a bit difficult. For example, it's like struct and then the name of the struct, the data type, the variable, let's say our struct. Or I don't know. And then we open the brackets, right? And then we have this symbol, I don't know how it's called, at the very end, right? And then in the struct, we can create anything as we want. For example, int x, int y, double, which is like 314, let's say. We can also like set the numbers already in the right? I guess. And so on, so on. Like we can also have pair, anything. And then, as it comes to like actually getting the variable, right? We, instead of writing like int, struct or something, we write down the name. Our you see? We have already there. Equals, not equals, sorry. And then we, let's say, the name is A, okay? And then when we try to access the information inside, we'll see A dot T, the pair, X, Y. So it's not first, second, there's no first, second, right? Because there is no like sequence. It just has the set of everything. Okay. It's just brief, let's say, coverage. Later on we'll see if we use it or not, how you use it. Anyway. So, the basic data types and everything aside, with also like the binary operations and the binary system and everything, we'll move towards our first thing, big step, which is going to be conditions, if else. So far what we were doing is just like linear, the program would be like just executing everything on order, and what we write it will do everything like that. So, but we can also support conditions. As, for example, let's say we have input of x. They give us a number x, and then we input the x, right? And then the problem tells us to check if the x is, let's say, positive. We print what? We print positive. If the x is negative, we print negative. If the x is 0, we print 0. And we can use the if condition to do this, right? So the syntax of the if condition is the if, right, brackets, in which we are going to write down the condition. And then after that, let's see, let's say x more than 0. This is the condition, right? And after that, so if we don't put any brackets, right? If we don't put any brackets like this, it is going to just let's say have the body of if, the next line only. As for example, cout a something. So here, let's say it's -2. Nothing happened. If it's 0, nothing happens. And if it's, for example, 5, yay, right? So the body is this. So if we, for example, put another, let's say, cout double yay, something. Is it going to work the same way as like yay, double yay, and then in other cases nothing, right? Is it? So for example, if we do 5, it's going to print yay, double yay, right? But if we do -2, it's going to print double yay. Why? Because in C++, not as in Python, you have to set the, let's say, the body. We have to mention from where it starts and where it ends. Because otherwise the default is the next line, and that's it. As for example, in Python, if we would like write this, it would do everything correctly, right? Because it's in one line, but no, in C++ it's not like this. So in C++, we are also putting brackets, which are this special type. And with this, we can like you can see, it's like it's also lighting up, right? So it's the beginning and it's the end. And then if we put this in a bracket, it's going to be one body, right? And here you can see that, for example, if I do like -2, or no, if I do 5, yay, double yay, right? And if I do -2, nothing happens, as it should. So the if operation is like the condition is either true or false. Do you remember from the previous class there was like a bool, the type bool, which is like either true or false, 1, 0, nothing else. And then in if the condition executes, like it goes through the body only if the condition returns true. So for example, if we would like, let's say, output the same, like x more than 0, greater than 0, what do you think it will print?
True.
Exactly. 1, which is true. It's like, right? And then if we did like, for example, -2, 0. So 0 stands for false. Anything else than 0 stands for true. So if we put, for example, in our if, for example, just instead of like some condition, we would just put like 2, for example, or like, I don't know, some number. Is it going to work?
No.
Yes. Because its number, it's either false or true, and then as I said, false is only 0, and then anything else is considered true, as far as it's not 0. So we just print the number, it doesn't really matter what, and it goes through, right? Because it's true. And then only if we put 0, it's not going to enter any time. Even if it's like more than no, right? And then in the okay, we'll talk about this later. So let's say we have the greater than 0 part, right? Okay, what about the rest? What about the 0 condition, and what about the, okay, let's not talk about the 0. Let's say if it's greater or equal to 0, it's yay, and then otherwise something else. So now we have like cout greater or something, and then otherwise, or positive, Otherwise, what? How can we do the rest? Like, okay, if it's not, if it's negative. Yes. So else is the next condition. Like if it's not if it's not true, it goes to next. If there is nothing, it just skips. Like there's nothing. But then if there's else, it always executes else. Right? So let's say, okay, negative. So if we type, for example, 5, pause. If we type 0, pause. If we type -3, negative. So in the case of it not entering here, it will go next and it will see, oh, else, do this. Okay. And what if we want to have more conditions? Okay, like if it's not like, let's say we also have to also check the 0 part, right? So if it's more than 0, it's positive. Otherwise, what? We also have to check if it's 0 or if it's negative, right? So what we could do is like, for example, else, and then in else we have another if, right? Is equal to 0, and then we print out it's 0, and then another else. In this case, look. If it's 0, it's 0, else it will work. Actually, it will work, but it's not the most clear implementation at all, because instead of doing this, we can have something called else if, right? So the way it works is else if, again condition, because with the else we don't have any condition brackets, right? Look, for else it's just else and then the brackets. For else if, we also put condition. So if the first condition of if, for example, x greater than 0 doesn't work, it's false, it goes to the next one and it checks this one. If it says else, it just does that, and then if it says else if, it checks the condition over here. For example, x equal to 0, so it's 0. Or if it's not 0, it goes further, else. So if it's not positive, if it's not 0, it's negative, right? Yeah, basically. Works. So nice. What if, for example, I want to have another problem? We have two numbers, x and y, and then we have to check if they are both greater than 0. We print yay, and otherwise we print meh, something. So how we can do that?
And use and.
Use and.
X greater than 0 and y greater than 0.
Right. So if we didn't know and, we would type like, for example, like if x greater than 0, then like if y greater than 0, right? And then cout like yay, and then else cout like meh, right? And then here just else and like cout something like this. But we have nice things called, I don't know how it's called. Comparison of, no. Anyways, some things to use. For example, if x greater than 0, so in Python we would write and, right? Right? Yeah, but in C++ it's not and, it's a symbol.
And.
And, right? We need to be very careful to not put only one and, because its binary operation is different. And then and is the end, right? So in this case, let's see, if we type in, let's say 0 and 10, meh. If we type 5 and 7, yay, because they are both in the same condition with the end. They're both greater than 0, so yeah, right? So other than end, we also have, for example, what? Or, right? So again, not the same as Python. In C++, it's this. And for example, let's check how it works. This condition, how it is going to work is basically, if any of the conditions are true, it will go through the yay. Otherwise, if none of the conditions are true, it will go through meh. For example, if none of the things are positive, like -1, meh. But then, for example, if we have like -1 and 5, it will look like, okay, this one is false, go through the second one, see. And then we have not. Like in Python, it would be like is not something, right? But in C++, it's the symbol. Right? And then what it does is basically just convert it, right? So if we do, for example, if you want to check if the number is not 0, right? Only that, for example. If the number is not 0, we just print yay, otherwise we don't print anything, right? So we can do like x equal to 0 or, sorry, no. So we have to write, like we have to answer yay if the number is not 0, right? So we could write, for example, x. So this is regular, like equal is like equal, right? So in C++, if it's not equal, it's like this. So and then, for example, if we want to check it like the regular way, not the regular way, sorry, to just like, for example, the false and true thing, right? So if we just print it like this, so if it's 0, it's going to print nothing, and then if it's not 0, it's it's true, so it's going to print yay, right? So for example, 6, yay, because it's true, and 0, nothing. And if we put the not operation here, what is going to happen? The exact opposite. So if the, I just double tap, that's fine. And for example, 0, 0 is false, right? But the node is going to convert it to true. And then anything else, for example, 8, is going to be converted to false. Okay. And also we have to be very careful in terms of the equal operation, because if we put, for example, only 1, it is like the static number, like when you set a number or something, right? It's different. It's not like comparison, right? So always 2. Okay. So ideally we would also cover loops for a while, but not this time because it will take time. But we'll cover it in the next class. So for the whole thing that we learned today, in the code courses, the link that I shared at the beginning, or from the next, I think, previous class, right? Just a second, I'll try it again. So this problem set is pretty much easy problems that are not requiring anything further. For example, let's see. So here we can see that, for example, the sheet 1 is like data type conditions, right? And then the sheet 2 is loops. So we don't know loops, we are not doing it right now, but we can, I think, fully finish the full problem set of first one, right? And then it would be very nice if you could practice during the free time at home, and fully solve the whole problem set, which is like 20 problems. It's it's gonna be very simple, like the same type, just to implement and to, let's say, try the knowledge in practice. So I'm printing the link in the group chat for the whole problem set. I haven't like checked every single problem here. I checked like the first half or something. It's normal. You can try. If you have any questions, you can ask. And I think that's it. If you have any questions, please reach out, ask. And yeah. Thank you very much. Bye.